Template metaprogramming is a metaprogramming technique in which templates are used by a compiler to generate temporary source code, which is merged by the compiler with the rest of the source code and then compiled. The output of these templates include compile time constants, data structures, and complete functions. The use of templates can be thought of as compile time execution. The technique is used by a number of languages, the best known being C++, but also Curl, D, and Excel. Template metaprogramming was, in a sense, discovered accidentally, see History of TMP. Some other languages support similar, if not more powerful compile time facilities, but those are outside the scope of this article. Components of template metaprogramming. The use of templates as a metaprogramming technique requires two distinct operations: a template must be defined, and a defined template must be instantiated. The template definition describes the generic form of the generated source code, and the instantiation causes a specific set of source code to be generated from the generic form in the template. Template metaprogramming is Turing-complete, meaning that any computation expressible by a computer program can be computed, in some form, by a template metaprogram. Templates are different from macros. A macro, which is also a compile-time language feature, generates code in line using text manipulation and substitution. Macro systems often have limited compile-time process flow abilities and usually lack awareness of the semantics and type system of their companion language. Template metaprograms have no mutable variables, that is, no variable can change value once it has been initialized. Therefore, template metaprogramming can be seen as a form of functional programming. In fact, many template implementations implement flow control only through recursion, as seen in the example below. Using template metaprogramming though the syntax of template metaprogramming is usually very different from the programming language it is used with, it has practical uses. Some common reasons to use templates are to implement generic programming or to perform automatic compile time optimization, such as doing something once at compile time rather than every time the program is run. For instance, by having the compiler unroll loops to eliminate jumps and loop count decrements whenever the program is executed. Compile time class generation. What exactly programming at compile time means can be illustrated with an example of a factorial function, which in non-template C++ can be written using recursion as follows. The code above will execute at runtime to determine the factorial value of the literals 4 and 0. By using template metaprogramming and template specialization to provide the ending condition for the recursion, the factorials used in the programmer ignoring any factorial not used can be calculated at compile time by this code. The code above calculates the factorial value of the literals 4 and 0 at compile time and uses the result as if they were pre-calculated constants. To be able to use templates in this manner, the compiler must know the value of its parameters at compile time, which has the natural precondition that factorial value can only be used if x is known at compile time. In other words, x must be a constant literal or a constant expression. In C++ 11, syntax, a way to let the compiler execute simple constant expressions, was added. Using syntax, one can use the usual recursive factorial definition. Compile time code optimization. The factorial example above is one example of compile time code optimization in that all factorials used by the program are pre-compiled and injected as numeric constants at compilation, saving both runtime overhead and memory footprint. It is, however, a relatively minor optimization. As another, more significant, example of compile time loop unrolling, template metaprogramming can be used to create length-n vector classes. The benefit over a more traditional length-n vector is that the loops can be unrolled, resulting in very optimized code. As an example, consider the addition operator. A length-n vector addition might be written as: when the compiler instantiates the function template defined above, the following code may be produced. The compiler's optimizer should be able to unroll the for loop because the template parameter length is a constant at compile time. However, take caution, as this may cause code bloat, as separate unrolled code will be generated for each n vector size you instantiate with. Static polymorphism. Polymorphism is a common standard programming facility where derived objects can be used as instances of their base object but where the derived object's methods will be invoked, as in this code, where all invocations of virtual methods will be those of the most derived class. This dynamically polymorphic behavior is obtained by the creation of virtual lookup tables for classes with virtual methods, tables that are traversed at runtime to identify the method to be invoked. Thus, runtime polymorphism necessarily entails execution overhead. However, in many cases the polymorphic behavior needed is invariant and can be determined at compile time. Then the curiously recurring template pattern can be used to achieve static polymorphism, which is an imitation of polymorphism in programming code but which is resolved at compile time and thus does away with runtime virtual table lookups. For example, here the base class template will take advantage of the fact that member function bodies are not instantiated until after their declarations, and it will use members of the derived class within its own member functions, via the use of a static cast, thus at compilation generating an object composition with polymorphic characteristics. As an example of real-world usage, the CTP is used in the Boost iterator library. Another similar use is the Bartone-Uranakman trick, sometimes referred to as restricted template expansion, where common functionality can be placed in a base class that is used not as a contract but as a necessary component to enforce conformant behavior while minimizing code redundancy. Benefits and drawbacks of template metaprogramming. Compile time versus execution time trade-off. If a great deal of template metaprogramming is used, compilation may become slow. Section 14.7.1 Temp-inst of the current standard defines the circumstances under which templates are implicitly instantiated. Defining a template does not imply that it will be instantiated, and instantiating a class template does not cause its member definitions to be instantiated. Depending on the style of use, templates may compile either faster or slower than hand-rolled code. Generic programming. Template metaprogramming allows the programmer to focus on architecture and delegate to the compiler the generation of any implementation required by client code. Thus, template metaprogramming can accomplish truly generic code, facilitating code minimization and better maintainability. Readability. With respect to C++, the syntax and idioms of template metaprogramming are esoteric compared to conventional C++ programming, and template metaprograms can be very difficult to understand. Metaprograms can thus be difficult to maintain by programmers inexperienced in template metaprogramming. See also, substitution failure is not an error, metaprogramming, preprocessor, parametric polymorphism, expression templates, variadic templates, compile time function execution. References. E. O. Seneca, Ulrich W. Generative Programming, Methods, Tools, and Applications. Addison Wesley. ISBN 0-201-30977-7. Alexandrescu, Andrei. Modern C++ Design, Generic Programming and Design Patterns Applied. Addison Wesley. ISBN 3-8266-1347-3. Abrahams, David. Gertivoy, Alexei. C++ Template Metaprogramming, Concepts, Tools, and Techniques from Boost and Beyond. Addison Wesley. ISBN 0-321-22725-5. Van der Voorde, David. Joe Suttis, Nicole IM C++ Templates, The Complete Guide. Addison Wesley. ISBN 0-201-73484-2. Clavel, Manuel. Reflection in Rewriting Logic, Metrological Foundations and Metaprogramming Applications. ISBN 1-57586-238-7. External links: the Boost Metaprogramming Library, the Spirit Library, the Boost Lambda Library. Veldhuizen, Todd. Using C++ Template Metaprograms. C++ Report 7, 36 €43. Archived from the original on March 4, 2009. Template Haskell. Bright, Walter. Templates Revisited. Koskinen, Johannes. Metaprogramming in C++. Attardi, Giuseppe. Cisternino, Antonio. Reflection support by means of template metaprogramming. Burton, Michael C. Griswold, William G. McCulloch, Andrew D. Huber, Gary A. Static Data Structures. Cite Xerox, 10.1.1.14.5881. Amjad, Zieshan. Template Metaprogramming and Number Theory. Amjad, Zieshan. Template Metaprogramming and Number Theory, Part 2 inches. A library for Lisp-style programming in C++.